Hi everybody. Good morning. Guy Hendricks here. Avia. I know most of you. Thanks a lot for joining us for this first VECMAP webinar. I hope you have a good time. We're trying to keep to the time limits. Well, you know, we've been launching this concept of webinars because we think it's going to be of great help for the people who want to use VECMAP to know a bit more about spatial modeling. It's our intention to have a new webinar every 6 weeks, and each time highlight special topics which help you in spatial modeling. All participants should on their screen have somewhere on the top left a Q&A button. So please, you're all invited throughout the webinar to ask questions through that Q&A chat menu. And then we will answer all these questions at the end of the webinar. I would like to introduce Cedric. Cedric is is leading our R&D group. He's an environmental engineer. Most of you also know him, I suppose, and he's very much specialized in remote sensing, spatial, and mathematical modeling. That is, of course, quite important when talking VECMAP. But in addition, he also has a strong background in ecology, ecosystem services, this kind of stuff, which of course is quite interesting when you want to understand the outcomes of your models. This first topic is addressing an issue which we've seen quite often actually. People have historical data sets. These data sets have been collected in various ways and are not homogeneously distributed. They have not been planned. They come from different sources, and then you end up with clusters. So what can you do? What should you do with these clusters to avoid them affecting the quality of your spatial model? So Cedric, the floor is yours. Please, to all, enjoy the talk.
Thanks, Guy, for the introduction. Let me share my screen. So everybody should be able to see the screen now. So I will be talking about, like he said, about addressing clustering issues in historical data sets, which you want to use for modeling in VECMAP. So this is just an introduction to the clustering. Given it's a 20-minute webinar, it's not possible to do a tutorial in such time. So I will give a couple of examples of techniques that you can use to deal with clusters in your data sets. So I will discuss the two by far most used techniques to deal with these clusters, and then I will for each of the groups I will give a quick and dirty example which you can use for presence absence data to have a quick test to see how much of a difference something like that would make. It's important to keep in mind if you do this type of pre-processing for your data, that there's no one technique that will work every time. It's always dependent on your data set. It's always a bit dependent on what your research question is or what you want to tell with your model. So I'm not going to tell you this is a technique you need to use, because that's that can vary significantly depending on which type of data you are using. So as Guy already said, this is part of our VECMAP webinars, where VECMAP is our software package which deals with everything from data collection to modeling and everything in between. With this modeling component, you can model newly collected data, historical data, with different types of models, so both statistical models, machine learning models, depending on also on your data actually, and which type of data model works best for your data. The reason why we start from historical data is because modeling is a circular process. So it's not the endpoint. So if you model the data that you have, then you can do a gap analysis and see where you need to collect more data to make a better end result. So that's also why you see on the right we present our VECMAP components in a circle, because it always feeds back to the beginning. So historical data sets, we use this as an example. Here, I will be talking mostly about presence-absence data, but it also applies to abundance data. And historical data sets are useful because of the time series they have. So you can create a multi-year data set, you can look at individual years, you can compare the two to see if certain years are exceptional compared to other years. It all depends, of course, on your research question. One of the issues that comes with historical data sets is, for example, if they come from longitudinal studies, is that you have yearly points for the same location. So you have a quite a strong cluster of points on roughly the same location, or roughly the same covariate values. That's what it basically comes down to. And that can skew your distribution model quite a bit. So, for example, if you have in your area 90% of the area is absence and only 10% is presence, if you don't correct for that, if your model predicts 100% absence, then at 90% of the time it will be correct. So statistically, 90% model looks pretty good, but of course it's useless as a real life output. So the main background why you have to deal with clustering in data sets like this is usually sampling bias. So it's almost every spatial data has a bias in it. Basically every spatial data has bias in it, and it's due to a couple of different reasons. The main reason is because you never actually really do truly random sampling. You always either prefer certain land cover classes. There are logistical things you need to factor in, accessibility. For example, you can't just sample a military domain, for example, or in a private property of somebody. And budget constraints is something we all have dealt with in the past. So even if you want to do a random sampling, you always introduce some type of bias, because even if you say, I'm just gonna spread out randomly with sampling points over the area, you're still gonna end up in a situation where you can't access certain ones. Then you need to take a point that's closest to that one, etc. So it's not always a huge problem, but it's always there. So bias correction is something that's always recommended. So I will give some data examples throughout this webinar. The data that comes from that I will show, it comes from a paper that we is now in Press and Parasites. It's been accepted but not yet published. That's titled "Constraints of Using Historical Data for Modeling the Spatial Distribution of Helminth Parasites in Ruminants." It's a presence-absence data, or the part that I will show here is presence-absence data of Dendriticum in ruminant livestock in Italy. It was a data set that was kindly provided by Kremopar for the MSc of one of our students here. The modeling that I will show here is done in VECMAP. It was a machine learning technique called random forest that we used in this one, but the pre-processing of the data set has been done largely in R or QGIS by the MSc students. I just used this example because it's a common problem, a common data set which has this problem. It's from surveillance program, longitudinal studies, etc. So the data itself, just really quickly, it's presence absence. So there was also absences included, which makes it a bit easier for this example because we didn't have to produce pseudo absences. It has quite a large set of data, so we can show a couple of different things. And then just really quickly, because I will show some distribution outputs, is the covariates we used. We used 39 covariates in total, not for each model one, of course, which are mostly Fourier transformed data at a 1 kilometer resolution. It's a fairly standard data set, that one, nothing special to say about it. So just to illustrate the data, as you can see, it's spread out over Italy, but you see that there's a very strong cluster in the southern part of Italy, which is also where Cremopar is located, so quite logical, and that most of their longitudinal studies, for example, is something you see often, that longitudinal studies are conducted in the area of the conductor. So as you can see, there's already also included absence data, which is pretty useful. So you don't need to create pseudo absences. So just something that I want to mention before you do any type of analysis, something I always recommend and is to check with the data you have and with the covariate set you have, for which areas you can actually make a reliable prediction. So in this case, we were interested in Italy. But given that you always have the sampling bias, or just areas that were not particularly interesting for the conductor to sample, or there were some constraints why there can't be sampled there, usually you're going to have niche areas that fall outside your area that you can reliably make a prediction in. So in Italy, for example, it was the foot slopes of the Alps, the Po Valley, a couple of mountain regions, stuff like that. It's always good to do this, not only from a reliability perspective, but you will also see in one of the techniques that I will discuss later in this webinar for the declustering, is that your boundary is rather important. So this will also, you can create a mask based on this, so you can clearly define your area of interest, which is important for later on. So the mask is, if you are doing quite substantial modeling, the mask also will help reduce calculating time, stuff like that. So for this one, I just used an environmental space model and a technique called Mahalanobis distance, which is based on environmental distance. It's something also technique that is included in VECMAP to make this type of analysis. So something that's often a point of discussion is that people think that the more data you have, the better the result, which isn't always true, because if you have a large clustering of the of your data, you can actually get better results with fewer data than all your data, because declustering is basically a data reduction technique, roughly, not exactly, but it's easiest to understand to think of it as a data reduction technique. And I give an example of the data that I just showed you. So there are some techniques that you can apply to see how many points you need to have to make a reliable data set, which is something, for example, you would use if you are interested in individual years of your data set. So you can make an analysis for which years I can make a reliable individual yearly prediction, and for which years I cannot. So if you would just run the data straight without any declustering, we needed 758 presence points. So the presence points were the limiting factor in this study. So you always look at your smallest class. So if you then did the same analysis, but we first did some declustering, we already got better results with as few points as 165 presence points, which is significantly less. And that's basically done because if you skew your data, you need much more data somewhere else to compensate for that bias. So if you have a very much concentrated cluster, it will draw your model towards, and skew your model towards that covariate values. So you need much more data somewhere else to compensate. So it's something, some techniques you can do to check on that. And if you don't want to do a complex analysis, you can also just run your model a couple of times with subsets to see what is the difference if you don't want to do a complex analysis on it. So I'll just show you here. If you take a subset of the data, you see on the left we had 165 points, and on the right we had 415 points. We just compared two individual years here, and the final result is that the few data set has a similar output statistics as the final model that we built in the end, and that even though it has almost more than twice the amount of data in the model on the right, it performed significantly worse compared to the one on the left. So just one final thing you have to realize or think about before you start with your declustering techniques is, what do you want to tell with the model? Because if depending on which clustering techniques you do, you can, for example, use things like years, for example. So if you do a quite aggressive declustering, and you that can have influence on something like that. So always do it separate from presence and absence. That's pretty straightforward. But if you want to do, if you want to analyze certain trends or abnormal years or something like that, then it's best to first divvy up your data set in the parts that you want to discuss. So if you want to, for example, compare different years to each other first, divide your data set in years before you do the declustering, and then do the declustering on the separate years. It is something that sounds pretty straightforward, but it's often forgotten or overlooked. So the absence creation can be done before this clustering, depending on which type of declustering you want to do. But I will not go into too much, because it's a topic for a whole separate discussion, which is already difficult to do in 20 minutes. But that's something that you can keep in mind, that pseudo absence you can do before or after, depending on your data, your question, and your declustering technique. So, like I already said in the introduction, there's no hard rules, as every data set is a little bit different. There's a plethora of techniques that can be used, but they all roughly rely on the same principle, which is weighting your data for its spatial representativeness. So it's basically making a weight correction on your data. I will discuss the two most common group of techniques, which is cell declustering and polygon declustering. Which one you use depends a bit on your data and also the covariates you want to use. We'll come back to that later. And then which individual technique you use, it's also depend a bit on which model you want to use later on, because it all depends a bit on weighting your data, but also not every modeling technique deals as well with weights or and stuff like that. So if you're unsure, I always advise to run multiple techniques and multiple models and compare the results to build a more robust modeling technique. And it's always, of course, always a good idea to use ensemble modeling as well for your final modeling. So the first one that I will discuss is cell declustering, which is already a relatively old technique. It was first proposed in '83. And the technique is actually pretty simple. You just post a regular grid over the data, and all the occupied cells, you give them the same weight. So depending on the amount of points within an occupied cell, the points will have a different weight, but the sum of all the weights will be the same for each occupied cell. And you do that for multiple origins, and then you average it out over the different origins. It used to be that the amount or the amount of origins were relatively limited, like 3 to 10. But now with modern computers and calculating powers, you can use almost as many origins as you want. Like I said, it's a technique that has been around for quite a while, so you already have a couple of derivative methods that most of you will be familiar with, like the moving window declustering, for example. And I now present this a quick and dirty example after this for presence-absence data, but you, of course, can always use also abundance data with this. It's a couple of important things that you need to realize, but I can explain this to maybe based on the figure. Is that obviously your grid size will have an influence on your result. It's also something that you need to consider in a relationship with your covariates. For example, it's if you have a pixel size of let's say 1 kilometer in your covariates, it's not wise to use a cell size which is smaller than that 1 kilometer, for example. So keep a bit in mind what spatial resolution your covariates have if you pick a grid size. So here I presented the origins as roughly on a linear line, but normally you pick your origin points at random, and you just do them all over the place, and then create an average over the weights, and that will be your final result. A big advantage of this is, as you can see, that it doesn't consider borders. It's a technique based on occupied cells, so it doesn't really matter how your area of interest looks like, how far your points are from the border of your area of interest, etc., which will be a big difference with the Polygonally clustering technique that I will explain after this one. So if you are afraid of bordering problems, this is one that you can most likely apply better. So I just give a very quick example of something you can do, just to have a quick test if for presence absence data. It's something that I actually always do for presence absence data, and that's if you have multiple points in one pixel, just reduce this to a single pixel, a single centroid in the pixel, because values in the same pixel give this points in the same pixel give the same values, and this can already make a significant difference. So if I, for example, here you have a cluster of quite a lot of points. If you then reduce this to centroids, that will already help significantly with the skewness of the data usually. But this is also where you can see that it's, if you are interested in multiple years or in individual years, that you first need to divvy up your data in years. Because, for example, this can be different years or not, and not point in the same years, for example. So then you first need to divvy up before you do something like this. But this is or something that's very quick and very easy to do, something you can use to check already how what the influence will be of the clustering on your data sets. It is, of course, a very simple technique, so it's not something that will deal with very complex data sets, but it's something that I usually do with every presence absence data set I have, just as a good practice to do that. So then you have the second class of techniques, which is polygonally clustering. So while the previous one worked with a regular grid, this works based on polygons and polygons of influence, or sphere of influence of your points. The big disadvantage of this technique is that it's sensitive, well, actually very sensitive to boundary locations. But this big advantage is it's a very flexible method. One thing that you need to keep in mind is that depending on how complex you want to make your polygons, it can be computational expensive. So in this time, it usually doesn't really matter that much anymore. But if you have a very large data set, a very large area of interest, this could be could have an influence. So a very example that most of you will probably know is Voronoi polygons or Thiessen polygons, depending on what your original background is. But that's based on Euclidean distance, but you don't have to use Euclidean distance. You can have something, polygons with a meaning, like a land cover, or and work on based your number of points per stratum. You can use something like environmental distance plus an Euclidean distance. So that's depending on what your question is, of course. So just as a quick example, this is a Voronoi polygon where based on some points. But as you can see, for example, here in the top right, this is what I mean with bordering issues. So because of your border is a square around it, it will fill in the polygons until the border of your area of interest. So this can give introduce more bias as well, because it will give the size of the polygons here has an influence on or is directly correlated to the weight that it will give to the point. So something very important to realize with if you do polygon declustering is that you have to clearly define your area of interest. And that's also where that mask that I was talking about earlier about for which regions can your data reliably predict. It's something that's also important for something like this. So just as a quick example, something that you can do to apply this very quickly without a lot of hassle is doing a stratified subsampling in strata and then bootstrap over the different data sets and build an ensemble model out of it. Something that's very often used for this is, for example, land cover, that you per land cover polygon that you subsample in it for the points, build different data sets, build your different models with it, then create an ensemble based on those different outputs. But it doesn't have to be a single layer. You can combine multi-polygon layers to create your sets. This, while the previous quick and dirty technique that I said, I gave example to with the cell clustering, is something that is pretty safe to do. Here it can be a bit a hit or a miss depending on your data and the polygons that you use. It's also, depending on your questions, if you want to separate years and stuff, that will be a very important one to do first as well. So this is something that I usually use for checking, but you have to make, if you want to build your final model based on this, you do have to make sure that what the influence is and how it propagates through your different models. So, for example, just to give an example here, you have different polygons and where you have multiple points per polygons, and then you would just pick points in the polygons and create a data set, randomly pick another set of points in the polygon, create data set, build model, etc. Something you can also do if you first do your weight analysis, you can also then do your subsampling based on the weights, for example. You can go rather complex or very simple depending on what you want to do. So I'm running a bit over time, but I'll wrap it up. So these were just the two most used group of techniques. Depending on what you want to do, you're gonna have more luck with the one or the other. But there are much more techniques there are more techniques than the ones or group of techniques that I presented here, ranging from very easy to very complex. But like I started this webinar, each technique has its advantages and its disadvantages. So it's best if you're not sure, try a couple different ones, and always be open to adapt if you notice or somebody figures out that something's not going well. Just always worth to try with another technique and see what the result will be. Just as a quick output, if you then create a subset, you can then create a much better model which retains your nuance, is not black and white. This is just a quick test with a couple of quick and dirty techniques, but as I said, you can go quite complex with it. So just to conclude, it's just a short introduction to what you can do, but there's no right answer. Also, something that I usually advise is worth looking into other fields that deal with spatial data. For example, geology is something where they deal with a lot of declustering techniques. So if you're looking for a bit of inspiration, it's always worthwhile to check on a couple of other fields. It's also something that's worthwhile thinking when you do your next sampling strategy. If you have an idea of the bias already in your current data set and you want to sample additional points, something that also helps in keeping that in mind. And of course, always happy to help and advise or collaborate on problems like this. So with that, I'll finish here, and if somebody has questions, I'm happy to answer them.
Okay, thank you very much, Cedric, for I see that Rose is writing a whole half a chapter, which is great. Thanks, Rose. Hannah from Liverpool, which we know from since quite a long time. So thank you very much, Cedric, for your contribution. So I see here Thomas is asking two questions. He says, if presence and absence data are observed in the same cell, do you recommend to keep these contradictory observations or have to take a decision? And what kind of decision rules would you then use? You see, the question is, you've got a cell, whatever it is, and there is both presence and absence data in that cell. What do you do?
So that depends a little bit to what type of data you have. For example, take invasive mosquitoes, for example, and you're looking at an invasive wave or disease wave or whatever. Then I would create a rule that say that for presence has priority over absence, for example. If you're dealing with disease outbreaks, the presence and absence data can both be relevant, and then you can either keep them both in your data set and let your model sort it out, or you can use something in between. So that you depending on your question, or you split up your data set in different years, and work on an ensemble model afterwards. But that's a bit depending on your specific data set at that stage.
So to summarize, if I understand well, if you talk about a dynamic system which is spreading over time in a given area, you would favor presence data in all circumstances. And when it is a more existing situation within an epidemics where the disease is supposed to, it's not an invasive process, you would rather suggest to deal with the presence data separately, decluster separately presence data and absence data, and then let your model decide about how they are taken into consideration. Is that correct?
Yes, or you can also use a hybrid system of the two. But you need to look at at that point you need to look at a case-by-case basis. What is your data exactly, and what is the outcome you hope to achieve with your analysis.
And do you recommend to use spatial correlation procedures when planning or executing your modeling algorithms?
Always, especially with covariates, for example. Do a spatial autocorrelation analysis before on the covariates you want to use. It's also one of the reasons why we always recommend to use Fourier transformed covariates, because they produce uncorrelated components.
Thomas, is that okay? I mean, are you happy with the answers? I think you have to click on raise hand icon to be allowed to have your microphone unmuted. Anyway, you mean Frank is following up and will give you access if you need to. So there's a question from Hannah from Liverpool. Is it acceptable to select pseudo absences after declustering? I mean, the question of pseudo absences was not detailed here. We can have a special webinar on pseudo absences, but do you think it is possible to do that after declustering, or before, or do you need to do it before declustering?
So that depends a little bit. It can be done both, depending on your range of modeling methods and pseudo absences recreation, and also how aggressive of a declustering you want to do or you need to do. It's a bit difficult to answer as in a general fashion, but if you're unsure, I would suggest to do it. If you use machine learning, I would suggest to do it after. If you use statistical modeling, it's a bit depending. It also depends on how you want to create your pseudo absences. If you want to, for example, use environmental space, it can be both advantageous to do it before and after. But you don't have to do it before, or you don't have to do it after. They can both be done depending on your situation.
Yeah, because actually Hannah is suggesting that certain software packages only allow pseudo absences after knowing the presences. So that's part of the question, actually, I suppose. So,
yeah.
So Hannah, if you're happy, just say so in the chat. You want to add something, Cedric?
Yeah, that's the software packages. That's usually when they work based on background values. Where they also automatically create pseudo absences, which I'm never a big fan of, but it's something you can look at individually.
Yeah, I suppose so. Yes, right. Good. Olivier actually mentioned that there was an issue regarding the spelling of krigging. It's with one, it's an I and not an IE. And actually, I saw Bootstrap with a D. So. But that's, and it's our first webinar, so we'll be checking that in the next. But he's asking a question: how on slide 5, how does actually I don't mean Olivier, could you be?
No, so he's asking. He only looked. He was only present at slide 5, if I interpret it correctly. Yes. So he asked about the statistical techniques like krigging. So I had first put it in the webinar, but I removed it due to time limitations, and it's also krigging is something that's part in of one of the techniques in VECMAP. And LNDA uses a form of krigging to deal with clusters. But that's something, statistical techniques, that a very widespread type of techniques you can use. And that's highly, krigging sometimes works well, sometimes works bad. It works also on your sync point and your adjusted mean. So it kind of I use krigging for when your absences and your presence are rather well defined areas. So I usually don't use krigging when your presence and absence points are crisscross in between each other, and it's hard to delineate a strong area between them. So yeah, again, depends a bit on your data set, of course, and but it is definitely a valid technique to use, and depending on your data.
Okay, thank you. So then Alessandro is asking, you know, you have got the issue of clusters. I mean, historical data, there's plenty data somewhere and then missing data elsewhere. But what, when you don't have when your problem is not necessarily clustering, but simply the fact that you could not cover every area during your sampling effort? I mean, how would you address that issue?
So if I understand correctly, your question is how to determine where you want to do additional sampling, right?
I think so, yes.
So then I would do, if the issue is not clusters, then I would do a gap analysis. So when I very quickly here to create a mask is look for the data that you have now, for which areas do we actually have enough data to already predict reliably, create a gap analysis out of that, and then try to do your sampling in those areas that were not covered yet.
Well, this is good actually, because I mean it's a perfect topic, because that's the topic of our next seminar. Is a webinar is going to be gap analysis by Willy Wind. So we don't have to go into detail here, but that's definitely going to be the next webinar. I think, I mean, to add to this reply, the mask issue is also something which is of interest here, and maybe we can have a webinar specifically on determining the area, what Cedric was explaining in the beginning of his talk. I mean, how can you define which area is representative for my samples? And that is possible. You can do that, and then you have then you generate within your mat the areas where your model is significant and based on the observed presence and absence data, and the areas where your model cannot say because it's missing data because the environment is too different. And I think combined with what Cedric was replying, that should help you in future improving that aspect. I don't see any further questions. At any time, you can send us an email or directly to Cedric. No problem. We are always very happy to answer questions and to help people with spatial modeling. I would like to conclude here, unless there is another question popping up, by thanking Cedric, of course, for his quite clear webinar and explanation. It's the first for us too, so there was, I mean, I don't know what your expectations were, but we are quite happy. And also, of course, I also want to thank the organizers, Frank and Damien, which have been setting up all the technology behind this, and which will make available. Actually, this has been recorded, and it will be made available on a YouTube channel. You will get that link by email, so you will be able to watch it again if you want to. The next webinar, as I said, is planned within 6 weeks' time. It will be by Willy Wind, so it will be on the 2nd of July, also midday Central European time. And it will be about actually this issue of gap analysis. I mean, once you know, I mean, where should I go for more additional samples? And actually, Root, which is also on this webinar, and Mika from Finland, Root will also be presenting. We don't know the date yet exactly because we don't know about availability, but she will be comparing outputs, modeling Pogosta in Finland using Biomod 2 models and VECMAP models. So that's going to be a direct comparison, which is of particular interest. And later on, they also will address the issue of baseline tick maps using historical data and how to plan additional samples using that very specific example in Finland, which is quite interesting because it will require the user-specific data layers. So we always open for any suggestion for future topics. We will also very much invite you, if you have been using VECMAP in one way or another and you want to share this, your published results, we will actively contact people we think have been doing really interesting work to eventually contribute a webinar in future. So we would be quite open to accept all proposals. So I think I said everything I needed to say. Thanks a lot for all of you for following us, and see you next time. Have a nice weekend, actually. Bye-bye to all. Thank you.